place, and that's the way it would look if you were standing there. Here's an image of stuff we dug up in the scoop, a color image taken with the lamps. And here's an image. The scoop has like a funnel built into it, and it moves material down to the center, and then there's a step right before the end of the scoop. And this is that step, highly magnified. And there's the stuff, you know, that's caught on that little step. And we put the step there because it's right at our close focus, so that's where we want to keep the stuff. This is a microscope image. The microscope field of view is 1 by 2 millimeters. And this is a 2 by 2 millimeter section. It's 2 images spliced together. This is magnetic material. There's a magnet behind the target. And so after all the stuff falls off, the stuff that's magnetic gets stuck to it. So, and they can tell by the different colors which type of iron ore it is. This is a rack image of a dump into one of the TIGA. TIGA is a valve gas analyzer. So they would dump soil into there. Now this thing only needs like a thimble full of soil to work. And it's got a screen under the door so the big stuff doesn't go down into the little thimble. Well, we kind of overdid it. I mean, you know, that happens. You design the sequence to dig some dirt up and dump it into TIGA. You don't know how much you're going to get, so the next day after it runs, you get to see the results. And say, oh, well, okay, kind of overdid that one. So, but we had trouble getting enough dirt to go through the screen. What we found out was the soil at this site, even though it was composed of very fine particles, the dust on Mars is the same size as cigarette smoke. Cigarette smoke is 1 to 2 microns in size, and that's the size of the dust. The dust that's in the atmosphere that you see, that's 1 to 2 microns. This stuff was much bigger than that, and it's stuck together. Well, it was stuck together by something. It's similar to caliche in the Southwest, if you've ever seen that. It's a calcium carbonate cemented soil. And this had the same characteristics. Particles are very small, but they were all clumped together. And, you know, we did a lot of testing with very, very fine dust. We used baghouse dust from the local power plant. And we had to wear masks and everything whenever we opened the bag of this stuff, because it just started flying around as soon as you opened the bag. And we dig the stuff up and dump it into our little TIGA mock-up. And, you know, a ton of it would go through the screen, and we thought, wow, we really understand how to do this. And then we get here, and you dump the stuff in the screen, and the little thimble that's under it, and there's a funnel under the screen that goes down to a thimble. It says it's only half full. What? Listen, we got like a cup full of stuff on there. I mean, what's going on? It was clumped together. And then this is a dump onto one of the TIGA wet chemistry cells. There's a little funnel right here. And it's got a screen over it. And we dumped, and of course we got dirt everywhere. But when we got done, the whole top deck around these two instruments was just covered with dirt. I mean, we had trouble controlling the amount of dirt that we got. Toward the end of the mission, we got to take some fun pictures. What we called it engineering pictures. We wanted to see how much dust had accumulated in the windows and the lights, and if all the LEDs were still working. So they gave us a few kilobits of data, and we took some images. So we used the SSI to take pictures of the rack, and we used the rack to take a picture of the SSI. So there's a thermal probe that we stick in the ground that when you rotate the scoop out of the way so the SSI can look past it, this thing comes into the field of view. Can't word it, but this little circle glint in there, that's actually the reflection off the filter inside the camera. So the windows are still very clear. That's also a reflection of how little really fine dust there is at this site. There's just not fine dust. If you look at the Pathfinder pictures, there's lots of fine dust all over the ground. loose, fine, small dust. Not here. The other thing we did was, there was an experiment on there to measure wind direction and velocity. Now, it actually turns out it's hard to measure wind direction on Mars because the atmosphere is so thin. It's about 1/100 the atmospheric pressure of the Earth. So, you can't use a regular propeller type wind turbine or anything. There's just not enough air to move it. So they came up with this idea of putting, this is a little piece of like mylar, very thin mylar film rolled into a cylinder. And then there's a very, very flexible thread hanging it from this post. And this is on a mast that popped up on the other side of the lander from us. So we turned the camera around, aimed it at this thing. It was inside of our good focus, so we had to have a diopter lens in the filter wheel to image this stuff in focus. And you can see this, we took a whole bunch of images toward the end of the mission, and they had more bit budget. And we got to do like a little movie of this thing moving around in the wind. So these are two different stills from that, just showing. But it worked pretty good. It wasn't terribly accurate in terms of precision, but it was cheap. And all it took was some pictures to work. So the last thing is, Phoenix is done. I was writing reports and everything. And Mike Drake, the head of the LPL team, had asked me to design some cameras for an asteroid sample return mission. So I designed some cameras for him, did the optics and some mechanic stuff, and kind of gave him an idea of how much they would weigh and power and cost and that stuff, you know, based on all the cameras we built before. But then Phoenix ended. I had to go out and get a real job. So I went out and worked at Raytheon, which is a missile manufacturer in Tucson. And I worked there for 2.5 years doing test equipment engineering on missiles. Then Peter calls me up one day and says, they got selected for the asteroid sample return. Could I come and talk to them? I got there and I felt like it was in the Blues Brothers, putting a band back together. So I gave in and helped and joined the OCAMS team. While I was away, the target asteroid had changed. It was a much darker asteroid. The reviewers for the proposal thought their image exposure times were too long. They'd get blurring, spacecraft jitter would cause them problems, so they wanted to speed up the optics. So they speeded things up. So now the telescope, the long distance, was an 8-inch f3 Ritchie. The refractor with the filter wheel was a 1.5-inch f3.3, and the imager for sampling was f5.6. I had designed like an f11 system, and they said, "Wow, that's not nearly fast enough." So, and all the glasses for these cameras and the filters had to be red hard shot glass. We were going to be seeing 5 kiloradians of radiation dose nominal. That's what they expect. We're going to be in space for 7 years. Most of that dose comes from energetic protons coming from the sun. Regular optical glass like PK7, all that stuff, it'll turn black at 5 kiloradians. You don't get any light through it. Well, you get infrared through it, no visible light. So you had to use red hard glasses. And Shop makes a whole bunch of red hard glasses. Well, 4. So we've got 4 glasses to design our optics for.
So did you combine a couple of different types of the shot glass so you could make an achromat?
Yep. There's 2 types of flints and 2 types of crowns. So you get to mix and match those. We in this refractor, it's a 5-element refractor, and it has 3 glass types. The corrector for the Ritchie is 2 glasses, you know, a flint and a crown, and the f5.6 imager is 5 glasses, or 4 glasses, 5 element with 4 glasses. So this mission's going on right now. It launched in 2016. In 2018, it got to the asteroid. It's in orbit around the asteroid. The asteroid's not very big. I got a team of 3 engineers, so I didn't have to work my butt off. We built these telescopes. This is the PolyCam, it's called, the long distance imagery. It's basically an 8-inch f3 telescope. This was mostly designed and built, at least the optical tube assembly was built by Opt Sciences. There's a department on the university called Optical Sciences, and they designed and built this. We installed the detector assembly in the base and did some of the final wiring and outside, but other than that, they did most of it. It has a focusing mechanism. And the way they do focus is they move one of the elements of the corrector around to change the power of the corrector, and by that they can change the focus. And it uses a very novel mechanism. It uses what's called a roller net. So this is the movable lens. It's got a gear on the outside. The front part is threaded. It sits in, and it's got a spiral thread. It sits in 3 threaded rollers. So as you turn it, it screws itself up and down. It's very rigid. It's great for vibration. It's never been done on a spacecraft before. We got a lot of static from NASA about that. Why can't you just do something simple? Okay, well, the mechanical engineer in charge of this wanted to do this, and he made it work. This is the map cam. This is a 135 or 125 millimeter focal length f3.3 refractor, 5-element. It's got 2 elements up here and 3 elements back here. It's a titanium 1-cell, titanium filter housing. Titanium's wonderful stuff for putting lenses in because its expansion coefficient is very similar to glass. So we could keep this focus constant over temperature. This is the detector assembly. CCD is on the other side of this part of the board. That's the hole for the cold finger. These are the gate drivers. These are the clock generators. That's the power and control chip. These boards get wrapped around the thermal frame, and the CCD is down on the bottom there. And this is what's in the base of the cameras. There's a cold finger, has a strap going out to this radiator that keeps the CCD cold. When you power up the camera, the whole camera warms up, but you want the CCD to be kept colder. They're not very good low noise CCDs, so you have to keep them fairly cold. This radiator is to cool the camera, and then the sunshade.
Question?
Yep.
Why were reflective optics considered instead of refractive?
For that focal length, reflective optics would have been more difficult and heavier. Just because, you would have a secondary obstruction, or, we looked at making a Newtonian, but you still end up with a secondary obstruction. And the refractive elements were actually much simpler and lighter than the other stuff. Alternatives. This is the sample camera, the SAM-cam. And this is the mighty lens. It's just a little lens, but it's designed for close-up imaging. The filter wheel sits in front of the lens. And the reason for that is the filter wheel is not so much a filter as a protective cover for the lens. This spacecraft has the ability to make 3 sample attempts. And so they can fly into the asteroid, grab a sample. When they do that, dust is going to fly all over. They're expecting the whole science deck to kind of get pelted with dust and rocks and just general garbage. So they wanted good images of each sample attempt, so we had to put a fresh filter in front of the lens for each sample attempt. So they had 3 separate windows to project the camera. This is the electronics box. This is the first time we've had to design a camera that was dual redundant. This is an important camera for the mission because it has to find the asteroid as they're approaching it. They can't navigate the spacecraft accurately enough to just blindly fly us there. So they have to find it optically when they're like 100,000 kilometers away. And it worked fine. No, they did that, and they were actually pretty good on their navigation. We didn't have to make much course corrections. So this box actually has 3 slices, one to run the motors, one to run the CCDs, one to do power generation, and there's 3 more down here completely redundant. There's 2 sides to the spacecraft. It's still redundant. This thing has to be able to talk and get power to either side. Because if we have a failure on one side of our box, and they're still on side A of the spacecraft, we have to be able to talk B to their A. Or if they have a failure and they're on side B, our side A has to talk to their side B. So there's a lot of multiplexing of power and communication stuff. And we got to deliver them. Lockheed Martin, they put them on the spacecraft deck. What you see here is red covers over the optics, but the cover on PolyCam is more than that. The PolyCam tube assembly is made of Invar 36. It's a very low coefficient expansion material, and it keeps the focus from shifting as the temperature changed on the tube. If you have a Smith gas, you're all aware of what that means. Invar is a very soft material, and the walls in the tube are very thin. I can pick up the camera. I know where the strong points are. I can pick the camera up. It weighs about 40 pounds. I can pick it up by the rim up here at the top of the tube and the bottom of the sunshade. That's a strong point. You can pick it up and carry it around. But if somebody were to just walk up and grab the PolyCam and try and move it, they would crush the tube. It was that thin. So we designed an Iron Man suit to go around it with lots of handles so that they can grab those and carry it up there. All this stuff is red because it has to come off before flight. And this is the way it finally looks on top of the spacecraft. Everything's covered with MLI, multi-layer insulation. Our cameras are all covered. They leave the radiators. We leave windows in it so the radiators still get to see space. There's covers over the optics to keep the dust out. Otherwise, that's the way it looks when it flies. That's the back of the radar, or the communication antenna, the big dish. This is the sample return capsule. That's actually a cover, but the heat shield is under there. That lid flips up. The robotic arm for this is on this side of the lander. It's all folded up. The head will be able to reach in and deposit it in there, and then they'll fold the cover back down and leave orbit from Bennu and rerun it over the Earth, and it enters the desert over Utah in 2023. Got to go to the launch, but this time we're not on a Delta II, we're on an Atlas V. And much bigger rocket. We had lots of mass margin. Our cameras and electronics box kept gaining mass as we got more and more detailed into the design. And they came back, and we expected lots of blowback from NASA, and they just said, well, don't try that again. Don't do that again. We'll let you get by this time, but don't do that again. Which was amazing. But they had like 400 kilograms of mass margin they were holding in reserve because of the size of the rocket. I got to invite 10 of my family. We got to go to the VIP launch area. It was fantastic. But there was only like 1,000 other people there at the same time. Like, they had set up bleachers, they had grandstands all over the place, they had people in the buildings. It was the VIP launch site, but there was a huge crowd there. I actually got pictures. That's my picture of the launch this time. I got a picture of the booster floating away from the rocket. There's the 2 RE-180 engines pushing the thing down range. I ended up setting up right next to this guy here, Mike Reed, who's the guy that designed all the print circuit boards in our cameras and in the electronics box. Didn't plan that. He just ended up to be standing next to me and turned around and said, Mike, And we're very happy after it goes off. I mean, it's just a real relief. So this thing launches in 2016. In 2017, it does a flyby of the Earth, and it does that to tilt the plane of its orbit to match the plane of the asteroid. The asteroid plane is like 7 degrees away from the solar system plane. You can't get there easily with the rocket. You use up too much of the rocket energy to get there. So they do a flyby of the Earth bends the plane, the orbit up, so now it matches the asteroid, and you can rendezvous with the asteroid. While they were there, they took calibration images of the Earth, the Moon. This is a MapCam full-color image of the Earth. This is a PolyCam image of the Moon. And this is a MapCam image when they're further away, the Earth and the Moon together. So, yeah, just, I saw that and I said, wow. I mean, they're doing some nice stuff. The cameras are working. Images are coming out good. So we get it the middle. So the first thing that becomes apparent is this thing is a rubble pile. They believe it is a collection of debris from a much larger asteroid impact. And it just became gravitationally bound together, and it's going through space now. And you can see there's huge boulders on this thing that stick out. I mean, the surface gravity is very low. It's like thousandths of a G. The escape velocity is 3 inches per second. If you stood on the surface of your spacesuit like that, you reach escape velocity. You never go back. So, this thing's 500 meters in diameter, 1,600 feet, rotates in 4.3 hours. The spacecraft orbital period is 62 hours. That's how low the gravity is. It takes, 2.5 days to go around the asteroid, one orbit. Because they know the orbital period, they know what the gravity is, and know what the mass is. After they've got all these images, they do a very accurate shape model, and now they know the volume. So the first thing they figured out was the density. And the science guys weren't real surprised, but I was surprised. The density is 1.3 grams per cc. So water is 1 gram per cc. Typical rocks are 2 to 3.5 grams per cc. This thing is close to the density of water, but it's made of rock. So it must have a lot of porosity. And they think even the rocks themselves have porosity in them. They're conglomerations of other rocks jammed together and just lightly, crushed together. This is a mosaic of a whole bunch of PolyCam images. The next thing they discovered was the asteroid periodically ejects a bunch of particles out of its surface. This was taken with one of the nav cams. They discovered this by accident when they were looking for stars and trying to do navigation images, and they found there's extra stars in the fields. What's going on? Okay, these particles are lit up by the sun. They're probably grains of sand, pea-sized pieces, and they're kind of just floating away from the asteroid. They think they're micrometeorite impacts hitting the surface, and of course they get a debris flying back out. So the surface is just really rough. And even more surprising, there's no fine dust on the surface. I don't know why, but again, the science guy says, well, we kind of thought that might be the case. But, everywhere you look, there's a rock. Yeah. The smallest thing you can see is just a small rock.